my area of expertise is general machine design, but I'm also deputy manager of very well-equipped laboratory for material testing. I wish you all very pleasant stay in Serbia, and I wish us all very successful session. As you all know, this session should last, according to the program, for 2.5 hours. We have 7 papers in total, so you have roughly 15 minutes per paper to expose your research. And please turn off your cell phones, so we don't bother the person who presented the research. And I would like to ask you to complete these questionnaires at the end of the session. After all papers are presented, please fill in those questionnaires which are on my table. And I think we should start. First of all, I would like to ask our dear colleague, Mr. Camille Caizo, to present the paper titled Characterization of the Ductile and Brittle Failure of Thin-Walled Tubular Materials.
Thank you. My name is Camille Caizo. I'm a PhD student, and as he said, I'm working on the ductile and brittle failure of thin-walled materials. I'm a PhD student, and I'm working with 3 different supervisors, which are Mr. Jacques Demouche and Abougit El-Malki. Also, I have an industrial supervisor, which is Mr. Frenal, who is working for the company Autoliv. For me, I am working at the Research Institute of Ductile in France. So let's start with a short introduction of this topic. Well, I'm working on airbag, which is made from a gas generator, which is composed, of a gas generator and a bag. The bag is inflated by the gas generated with a pyrotechnic devices. So, the gas generator is made from, of course, a pyrotechnic devices, but also with a steel tubular chamber. And this chamber must be the key problem for the company. Why? Because simply, we have a steel tubular chamber made from an high-strength steel, using, of course, a low-carbon manganese steel, and with a benetic microstructure. There is a very thin grain size, close to 3 micrometers. Also, during inflator functioning, there is a dynamic loading of the chamber due to a pressure wave propagation through the chamber. And if it's not sufficient, you are in automotive industry, consequently you have to validate some specification, and the most critical specification is that inflator robustness must be ensured at low temperature, minus 60 degrees Celsius. So here you combine high-strength steel with very thin microstructure, high strain rate loadings, and low temperature condition. So brittle failure can occur, and this mode of failure is really critical. So we have to be sure that it do not occur. So that's why there is a need for experimental method adapt to tubular materials and able to characterize, of course, material behavior, ductile failure, and also ductile to brittle transition. That's why in my presentation there is 3 different points about characterization, ductile failure, and finally ductile to brittle transition. Also, to finish, I will conclude. So, let's start with the material characterization. First of all, I can only work with tubular specimen. Why? Because the steel supplier is not able to produce the same material onto a flat shape. So consequently, for quasi-static tensile test at room temperature and low temperature, I have to use, of course, tubular samples with a defined geometry. Also for Split-Tompkinson tensile tests, which are made in order to characterize the strain rate sensitivity of our material, we have to deal with tubular samples. That's why we have developed in my laboratory a new methodology in order to apply tubular sample onto Split-Tompkinson tensile tests. If you have any question, I could answer at the end of this presentation. And finally, with these 3 different kind of tests, we were able to identify this Zewili-Armstrong model and also these parameters. Then, when material behavior were fully defined, we start to study the ductile failure properties. And in order to study this one, we have to use, of course, notch sample, but here we are using curved notch sample. So there was many simulations, firstly, in order to determine the 3 different notch radius that we will use. And of course, as we are using 3 different radius, there is 3 different maximal stress triaxiality and 3 different stress triaxiality film. When design were stopped, we proceed to the test and we get the following results. So here you have the curve force versus displacement for the 3 different notch radius of our sample. Then firstly there is pop-in phenomena which occurs during our test. This is due to the very low ductility of our material. Also, but in order to determine the maximal displacement, which is not given in this graphics, we were used a different approach in order to have height sampling frequency on our test. So, with this kind of with this kind of methodology, we were able to define the maximal displacement at coalescence, and then we were able to determine much better the damaging parameters. So, with this test, of course, as there is pop-in phenomena, we have to check if fracture surface are purely ductile or if there is any cleavage on this. So, sorry, micrographics analysis showed that there is only ductile fracture surface, and there is with the presence of two-sized dimples. This is due to the mechanism. This is due to the damage mechanism of our material. Then there is a second point, which is that micrographic analysis showed that fracture initiates at, of course, maximal stress triaxiality location in accordance with our numerical simulation. So this is in good agreement with our previous calculation, and will be a significant point. It will be it will be great for us, because with this new kind, due to the curved sample geometry, we have some doubts about the validity of those tests. So as the kinematic of fracture were validated, we can start to identify ductile failure model. We are using the famous GTN model, where you can find the expression of the yield surface here, and then we get 3 different modifications. The first one consists in splitting the porosity evolution in 2 parts. One part is from void growth, and the other part from nucleations. And for nucleation model, we were using a very recent theory proposed in also recent PhD thesis, less than 1 year. If you have any question, I will answer at the end of this presentation, of course. And then we will define a coalescence criterion with the Thomathan model. This is not a strictly criteria, because you didn't find, it's not possible to find a critical value has such criterion. It's an implicit criterion. Then, using this model, we inject this equation inside a finite element analysis simulation, and we compared the experimental results to the numerical simulation results. As you can see here, the fits were quite good. So we were satisfied with this fitting, and then we tried to validate this model. So, to validate this model, as well in an industrial context, we have to use a different test with no link with the previous test. So, here we are using buzz test. This is a really simple test because we are using an internal pressure applied into the chamber, and we increase this pressure up to rupture. When rupture occurs, we are measuring the pressure level, and then we compare this level with the level obtained with the simulations. Then finally, results show that we have less than 5% of difference between experimental and mechanical simulation. So, with this result, we can say ductile failure identification is finished. So, let's start to talk about the ductile to brittle transition. I don't know how many times.
Minutes.
5.
5 more minutes.
Yeah, perfect. So, in order to identify ductile to brittle transition, we have some difficulties because here we are using, of course, sharp impact test. But as you know, in order to have sharp impact test, generally we are using coupons. But here we have a thin walled tube. So we have to define a new sample geometry, and here we are using a ring Sharpie impact test. Of course, a specific devices in order to correctly maintain the sample were developed, and then we were trying to realize some tests. Also, there is 2 diameters tested, a 30 diameter which correspond to the material at the initial state, and then a second diameter which is 21 millimeter, which correspond to a critical part of the structure. And for our industrial company, it will be very interesting to be focused on these 2 samples. So, also, we have a last really important point, because the impact forces measurement were done using not a classical instrumented Sharpie hammer, but we have mounted strain gauge on the hammer in front of the sample. This gives quite good result, and if you want to discuss about this method, I will answer you at the end, of course. So, then, once Sharpie test samples were defined, some tests were done with these 2 diameters. And as you can see here, there is really 2 different curves, and of course, 2 different ductile to brittle temperature transition. This is due to one part, the sample geometry, and also this is due to the mechanical manufacturing process, because in order to obtain the 21 millimeters diameters, there is a cold deformation. So, of course, there is this result, and it's really hard to compare this one, but there is one important fact about the resilience at room temperature. As you can see, resilience is divided by much than 2 times. So, between the 2 materials, which is initially exactly the same state, there is a very large gap. So, we try to explain why there is this gap. And in order to explain this gap, we will study the surface, the fracture surface using sim observation. So here you have the observations of the 30 millimeters diameters, and as you can see at room temperature there is purely ductile failure behavior, while for the lowest diameter, 21 millimeters, there is only this part of ductile failure, and this is only and purely brittle failure. So here there is an interesting result, because when we have exactly the same initial material and we provide a large pre-strained field to samples, his behavior totally changed. So we have to explain and to explore these ways in my study. Also, let's take a look at the result of forces measurement during a Champy impact test. Here, I only used the result of 30 millimeters curve, 30 millimeters ring diameter, and there is no classical force deflection curve for Champy impact test. But there is one phenomena which is subject to discussion. What is this? Because this appears for each temperature, and even if there is only brittle failure. And using numerical simulation, we were able to prove that this phenomena is directly linked to the sample geometry. Because when you are using a ring Champy test, a ring sample, sorry, while just before the forces increasing, there is a really short time during which the sample is repositioning onto the devices. So this was our conclusion. And then currently I'm working on the simulation of those Champy tests in order to determine which is the impact of the different diameters. So I will work with exactly the same materials. Thank you. For exactly the same material, and then I will compare the difference for the two diameters and the difference for two different pre-strain states. So that's why my conclusions are the following. First of all, I have to say that material behavior is fully determined using a wide strain rate and temperature ranges, and also for tubular material. Then, for the ductile failure, model is fully identified and validated. So this is quite good for our industrial and for us, because it allows us to start the ductile to brittle also characterization, but the study. And then, as our ductile to brittle characterization tests are well working currently, the outlooks of this work are the following. I have to do some numerical simulations and a lot of numerical simulation in order to validate or discard the different positions that we have made for the Champy test. And then finally, in order to keep the industrial context, we will apply this method to the entire structure of the gas generator. Thank you for your attention.